Okay, so let's talk about our second hypothetical rule, which is negation introduction. So we've already learned the basic idea behind negation introduction, which was sometimes called reductio ad absurdum, which means to reduce to absurdity. It's also sometimes called indirect proof. And where we've learned it is from refutation trees. So you'll remember that with refutation trees, what we do is we hypothesize the negation of the conclusion, and then we attempt to derive a contradiction. So that's what we do here as well. The difference is just that in a natural deduction system, when we succeed in deriving a contradiction, we're allowed to immediately discharge the hypothesis, just like in conditional introduction, and then we can assert that the conclusion is true. So let's see how that works. Now, this is actually a very common form of reasoning in ordinary life. Here's an example I like. I used to coach girls softball, and once one of my players, Megan, was complaining to another, Alyssa, that she was getting fat. These aren't their real names, by the way. So Alyssa responded to Megan saying this, Megan, you're not fat, because if you're fat, I'm fat. And I'm not fat. This is pretty easy reasoning to follow, isn't it? After all, these are junior high school students, and it's a very natural sort of thing for Alyssa to say. But we can formalize this. It's not quite formal yet. We won't formalize it in propositional logic, but we can formulate it more explicitly as follows. So Alyssa is saying, Megan, first of all, I am definitely not fat. Let's just get that clear. Now, let's hypothesize, as you say, that you are fat. Let's take that on as a hypothesis. Well, just look at us. We're totally the same. That's according to Alyssa. So that would mean that I'm fat too. And Alyssa's actually using the principle of identity here, which we don't have yet. That's a pretty straightforward idea. But this contradicts assumption one, that I am not fat. Therefore, hypothesis two is incorrect, and it follows that you are not fat after all. So quite a bit of complexity underlying this junior high school student softball player's reasoning. And this is exactly the form of negation introduction. So let's see why that is. Well, actually, this form of reasoning is extremely important in philosophy and logic and mathematics. There's a famous proof of God's existence, which you might have been exposed to if you took, say, introductory philosophy. It goes like this. God is the greatest conceivable being. Let's stipulate that that's just what God is, the greatest conceivable being. Now, let's hypothesize that such a being does not exist. Well, I can at least conceive of such a being as existing. So we hypothesize that they do not exist, but that doesn't mean I can't conceive of it as existing. So I can conceive of such a being as existing. But clearly it is greater to exist than not to exist. People have argued about that, but suppose it's true. Clearly it's greater to exist than not to exist. Hence, it follows that I can conceive of a being that's greater than God. But this contradicts assumption one, that God is the greatest conceivable being. Therefore, hypothesis two is incorrect, and it follows that God exists. So again, a straightforward reductio ad absurdum, or what we are going to call the rule of negation introduction. Okay, so let's see how this works formally. So as with conditional introduction, there are lots of obviously valid inferences we actually can't prove without negation introduction. For example, right now, prior to the introduction of negation introduction, we can't prove this. P yields not P. We have a rule, negation elimination, that allows us to derive this in the opposite direction. We can go from not P to P, but we can't show that P entails not P. We don't have a rule that allows us to do this. So negation introduction allows us to do this very simply. So assume P, and what we'll do is we will hypothesize the negation of not P. We'll hypothesize that this is false. Now, from your refutation rules, you know that you would ordinarily have to do is negate not P. But the rule, the hypothesis rule, allows us actually to hypothesize absolutely anything we want. Just like you're allowed to assume anything you want, you're allowed to hypothesize anything you want as well. So we're going to hypothesize, rather than not P, we're going to hypothesize not P, which is logically equivalent. So we hypothesize not P, and we immediately, of course, get a contradiction, P and not P. So we can assert that contradiction on line 3. You'll notice that in line 2, just as with conditional introduction, we indented, and now we're keeping that indent, right? P and not P by 1, 2, and introduction. So what we've done is we've said, if we hypothesize the negation, the opposite of the conclusion, we get a contradiction. And since we get a contradiction, we're allowed to assert that the hypothesis is false. So the way we do that is we have to assert, and this is required, we have to assert the negation of the hypothesis. So on line 4, we're now entitled to assert the negation of the hypothesis by 2, 3, negation introduction. Notice we've now taken away the indent, which means that we're going to drop a bar. So this is just like with conditional introduction, the way we treat hypotheses. And we're not done. Oh, yes, we are done now, right? Because we now have derived not P. So a very straightforward application of negation introduction. So let's go ahead and review that. First, we hypothesize the opposite of what we want to prove. In the refutation tree system, you'd be required to negate the actual conclusion, but we're allowed to write anything we like here, so we can just hypothesize not P. Then we derive a contradiction. And here the contradiction is just sitting there waiting for us. Typically, more work is going to be involved to get a contradiction. But any contradiction will do. You don't have to have any specific contradiction. So you're always required to write the contradiction as a conjunction on a line by itself. You can't just say, oh, look, there's a contradiction between 1 and 2. You have to take line 1 and line 2 and put them together as a conjunction. So you'll almost always be using the and introduction rule when you do this. Then, having derived the contradiction, you're now entitled to assert the negation of the hypothesis. So you look back up at the hypothesis and you say, what was my hypothesis again? Oh, it was not P. Okay, so now I can write not P, which fortunately turns out to be exactly what we were trying to get. So you must always literally do this, okay? Put a negation in front of the original hypothesis. That's a totally mechanical procedure. And then, just as in conditional introduction, you drop this line. And here, the justification ranges from the hypothesis to the contradiction. So here it's just 2 through 3, but in some other proof it might be 2 through 23. So the same rule applies as for conditional introduction. Specifically, you must discharge all hypotheses before you're done with the proof. And as I just said, it's important to understand that any contradiction will serve the purposes of the negation introduction rule. Specifically, you don't need to contradict the hypothesis itself. And we'll see how that works pretty quick too. All right, so let's just look at a few examples. This is just a summary of what I said if you happen to be looking at the slides. Before we look at an example, let me tell you what the most common error in negation introduction is. The most common error is to assert that two formulas contradict themselves when they really don't. For example, this is not a contradiction. Now, in the clear light of day, you can say, well, of course, that's not a contradiction. What would the contradiction be? Well, the contradiction would be this formula and its negation. So this negation would have to be on the outside. But when you're struggling to do a proof, you might just let hope cloud your judgment a little bit and assert that something is a contradiction when it's not. So just remember that the only thing that's ever a contradiction is this, some formula and its negation. Of course, this is a contradiction as well, the negation and the formula, but it has to be that one or the other of these. That's all. It's the only thing in logic that counts as a contradiction. So this rule, negation introduction, is really very powerful. It's the most powerful rule we have in many ways, and it can be used effectively where direct proof and conditional introduction don't help you out much. So really the only reason not to use negation introduction is just that sometimes the negation introduction proofs are long and unnecessarily long. So as a rule of thumb, what you should do is see if you can prove something directly, and if not, see if you can prove it using conditional introduction, and if not, then start thinking about negation introduction. These aren't mutually exclusive, by the way. We'll see pretty quick here that we often use negation introduction along with conditional introduction and other rules like or elimination, disjunction elimination. All right, so here's another simple negation introduction proof. It's a little weird because you're being asked to derive S from two assumptions, neither of which contain S. You might remember that a while ago I said that anytime you have a contradictory set of assumptions, you can prove anything. And so this is going to be a working example of this. You've got P and Q, and you've got not P. And because you have a contradiction sort of barely buried here beneath the surface, right? P you can get through and elimination. So you've got P and not P right away. Because you've got a contradiction between these two assumptions, you're going to be able to use negation introduction to derive just anything at all. So this is the method that shows why this is the case. So what we do is we hypothesize the opposite of what we're trying to prove. Opposite really isn't a technical term in logic, but it captures the idea. We're going to hypothesize the negation of S. So we're going to hypothesize not S. And then we're going to, as a result, as soon as you do this, sometimes you'll write on the side to remind yourself for negation introduction, to remind yourself why you've hypothesized this. That means you're looking now for a contradiction. Well, fortunately, that's pretty easy to produce. We've got P by 1 and elimination. And so we have P and not P. Now we have to write this on a line by itself. So we had not P here, we had P here. You can write P and not P, or you could write not P and P. Those are both contradictions. 2, 4, and introduction. So then we say, hurrah, I've got my contradiction, and that entitles me to assert the negation of the hypothesis. So now I look back up at my hypothesis. I say, what can I do now? Oh, I can assert not S. And then I can drop that line. So it's always the negation of the actual hypothesis, not something that's logically equivalent to the negation. You're not allowed to assert S here. You're allowed to assert not S. And so consequently, the last step here is just to assert S by negation elimination. This is quite common with negation introduction proofs to have to do that at the very end. Now this proof has a peculiar feeling to it because the hypothesis itself doesn't generate the contradiction. The contradiction is just already there, sitting there. And so when we hypothesize not S, it didn't really do anything as such. It didn't produce the contradiction. Well, what that shows you is that, oops, that should say, a little I missing there. What that shows you is that you don't need to produce the contradiction with your hypothesis. You only need to get a contradiction somehow, and any contradiction whatsoever will do. Okay, let's talk a little bit about the power of indirect proof. You could easily prove this proof in just one step. P and Q, therefore P, by and elimination. But it's important to see that you could, if you wanted to, also prove this indirectly. And that sort of testifies to why indirect proof is so much more general than any other kind of proof. So we we assume P and Q, and then we just hypothesize not P, right? Well, having hypothesized not P, we have almost generated a contradiction. We can put P again by 1 and elimination. We have P and not P, and therefore, just as before, we have not P, because we're negating the previous hypothesis by 2 through 4 negation introduction, and then our final step would be to assert P by negation elimination. So very, very similar to the previous proof. The point here is just that you didn't need to use negation introduction here, but it still worked. It's much longer than proving it directly. So try directly first. If not, negation introduction is your friend. It'll bail you out with just typically a little bit more work. Sometimes actually a lot more work, but it will get you there. All right, so here's a slightly more interesting application of negation introduction from P and not Q. Just one assumption, we're asked to prove it's not the case that if P then Q. This might look a little bit familiar to you, right? Because you know from your refutation tree rules that it's not the case that if P then Q goes to P and not Q. Now we're not proving it in that direction, we're proving it in the other direction. These are logically equivalent formulas. You can prove them in both ways. So what are we going to do? We're going to hypothesize the opposite of the conclusion. We could hypothesize it's not the case that if P then Q, but we don't have to. So we'll hypothesize the simpler if P then Q, and that'll prevent us from having to do the negation elimination at the end of the proof. So we have if P then Q by hypothesis, and now, right, this is for a negation introduction, right? So we're going to try to get a contradiction. So we have P by 1 and elimination, of course, and by conditional elimination, that gives us Q. So Q contradicts not Q. We have to put that on a line by itself in order. So this is important. I didn't really emphasize this before, but you can't just grab not Q out and create a conjunction, right? And you have to be using a rule each time. So the only way you can create this conjunction is by putting them both on lines by themselves. So Q and not Q. And that entitles us, having achieved the contradiction, Q and not Q, by 4 or 5 and introduction, we're now entitled to remove the indent and assert the negation of our hypothesis. So not if P then Q, and we finish by dropping the bar. All right. All right, so what I'd actually really like you to do here is stop and take a break and go back and look at the proofs that we've been doing on your own and try to produce them all on your own. And if you have a problem, then go back through the video and try to figure out what it is that you still need to learn. I'm going to finish this video with just one proof and some review questions. And this proof is rather interesting, and we can just go ahead and say it's somewhat difficult. It would be very impressive if you could figure this one out on your own. But it involves a kind of pattern that you're going to see later, and I want to introduce it to you now. So what we are asked to prove here is this. This is actually a very obviously valid argument. P or Q, not P, therefore Q. You can get that right off of a truth table. Also, P or Q, not Q, therefore P, right? This is a rule, famous rule that we call disjunctive syllogism, but in our system it's not a basic rule. It's one that we actually have to derive. So this is what we're going to do right now. We're going to derive this rule. Now, since we're doing a negation introduction proof, the normal thing to do here, you would think, would be to just go, okay, look, I'm trying to prove Q, so I'm going to go ahead and write 3, hypothesis not Q, right? That would be the obvious thing to do here. And then what you're doing, of course, is looking for a contradiction. So let's find a contradiction. Well, P contradicts not P, and Q contradicts not Q. So it looks hopeful at first, but you can't just pull P out. This is not an and, this is an or. So you can't just pull P out of here. And also, you can't just pull Q out either for the same reason. So it looks like we should be able to get a contradiction, but we can't by any rule that we currently have. So what are we going to do? Well, the answer is that this basic method right here, which is what you should think of initially, actually just isn't going to work. So what we need to do is something else. So what is that something else going to be? Let me just go ahead and erase this for a second. Okay, so how can we proceed? The answer is that we can proceed by or elimination, disjunction elimination. You have a disjunction here, and you're going to have to use it. And whenever you use disjunction, you want to be thinking about the possibility that you're going to have to use disjunction elimination. So let's go ahead and say, look, I'm supposed to get Q. Well, maybe what I can do is first prove, remember how the disjunction elimination rule works here. What we want really is disjunction elimination. What we want, we've got P or Q already, right? So what we want is if P then Q, and also if Q then Q. And if we have if P then Q and if Q then Q, then we can write Q, right? So we want to derive this first and then this afterwards. So let's derive if P then Q. So how do you do that? Well, you go back to conditional introduction, right? And you say, I'm going to hypothesize P, and I'm going to try to get Q. Well, fine. We hypothesize P, and now we're going to try to get Q. Well, is there any way to do that? Again, not obviously. So what are we going to do? Well, now think about negation introduction. What if we said, okay, what I want is Q, so I'm going to hypothesize again, right? A second hypothesis. I'm going to hypothesize not Q, and this time for negation introduction, right? So I'm trying to get Q, but I'm going to try to do it by hypothesizing not Q. So we hypothesize P to try to get Q for conditional, if P then Q. Now I want Q, but what I'm going to do is hypothesize not Q and try to get a contradiction. Well, I have a contradiction sitting right here, just as before, P and not P. So I can actually just assert that contradiction by 2, 3, and introduction. Okay? So having gotten the contradiction, I can now assert not Q and drop a line, right? Why not Q? Well, because that's the negation of this hypothesis. So I have not Q by 4 through 5 negation introduction. Now I didn't want not Q. What I wanted was, of course, Q, which I get by 6 in negation elimination. But now I've achieved my original goal, which is to prove if P then Q, right? I've almost achieved it because I hypothesized P and I derived Q. So now I can assert if P then Q, which is the first conditional we wanted, right? By, actually that should be 3, I made a mistake here, 3 through 7 conditional introduction, okay? 3 through 7 conditional introduction gives me my first conditional. So I've got if P then Q. Now the question is, how do I get if Q then Q? Well, that's a very strange thing, right? I mean, it seems like, well, if you have Q, you've got Q. Why would you even need to prove something like that? Well, occasionally you just have to, and it turns out to be incredibly easy. So what you do is you hypothesize Q, again, for conditional introduction or elimination. And now what you see is that you have Q, right? You've hypothesized Q, and as a result of having hypothesized Q, you have Q. That's what you're trying to get. So the hypothesis itself provides you with Q. So very oddly, but completely consistent with the rules, you can now assert if Q, then Q. Okay? So if P then Q, and if Q then Q here, if Q then Q is just 9 through 9 conditional introduction. Now, if this seems familiar, it's because we went through something like this in the review questions for the previous lecture on conditional introduction. Okay, so now we have if P then Q and if Q then Q, right? We can drop a line. So we have if P then Q and if Q then Q. Negation introduction only figured into the first leg. And having gotten both if P then Q and if Q then Q, we're now entitled to write Q by 1, 8, and 10 disjunction elimination. Okay, so that one's a little bit more complicated. We're going to get into, in the coming weeks, even more interesting versions of these. And this is where we really bring all the tools to bear on constructing our logical system. All right, so now we'll do some review questions. As in the previous lecture, you should, these are not multiple choice. These are questions about whether we're making a good or a bad inference, and you should try to explain to yourself your answer in each case. All right?